And today it's my pleasure to start not only seminar, but this is the first our meeting in this new semester. And the speaker is Valeriya Kotelnikova with some survey about new results in Karlin scheme. Please.
Okay, do you see my screen? Because yeah.
Yes, yes.
Great, yeah, because it was loading for a couple seconds, I didn't understand.
Yeah.
Okay, so first of all, I want to thank the organizers of the seminar, to Andriy and to Georgi, and to all of the listeners for giving such a platform for both young mathematicians and already acknowledged mathematicians to share their results. And this talk is special for me because I'm about to show you almost all of the results which I have proven during my short research career since 2021. To be more precise, it is based on 4 joint papers with my great co-authors Darek Burachevsky from Wrocław University, Sasha Iksanov from Taras Shevchenko National University of Kyiv, and Zahar Kablushko from University of Münster, where we were proving limit theorems for Karlin's occupancy scheme. But before jumping to those limit theorems, I want to introduce Karlin's occupancy scheme to you and also show which limit theorems have been known before. So let's start. Infinite occupancy scheme is also known as Karlin's occupancy scheme, and also you can meet a name an infinite balls in boxes scheme, but the core stays the same. And the core is you have an infinite array of boxes numbered 1, 2, and so on, and you throw balls into these boxes with probability P1 of hitting box 1, P2 of hitting box 2, and so on indefinitely. And you throw those balls independently of each other. Here, pk is a discrete probability distribution, and additionally, you assume that there are infinitely many positive pks. In terms of balls and boxes, this condition that infinitely many pks are positive means that there are infinitely many outcomes where a ball can fall with positive probability. And this explains the name why the scheme is called infinite, because you have infinite amount of boxes possible. And why the scheme is called balls in boxes, I think you figure it out, because we throw balls into these boxes. And why the scheme is called Karlin's occupancy scheme, I'm going to discuss a couple of slides later, while I'll discuss the contribution of Karlin to the research in the scheme. But as for now, let's look at one of possible realizations of the scheme. At first, at time 0, there are no balls, so all boxes are empty. Then at time 1, you take the first ball and it falls, for instance, into the box 100, and it happens with probability p100. At time 2, the second ball arrives and falls, for example, into the box number 2, and you continue this process indefinitely. And what do we consider in the scheme? We consider such random variables. When you have thrown n balls, we are concentrated on the number of occupied boxes, which we denote by kn, the index of the last occupied box, mn, and the number of empty boxes within the occupancy range, ln. And let's calculate those characteristics for this particular example. So first of all, we write everywhere index 5 because at this particular time in the scheme, there are 5 balls. Then the number of occupied boxes is equal to 3. Those boxes have numbers 2, 3, and 100. The index of the last occupied box is 100. And to understand what is ln, let me first define for you what do we mean by occupancy range. We mean the range from the first box to the last occupied. So the number of empty boxes in this range from 1 to mn is the amount of boxes mn minus the amount of occupied boxes kn. So it's just simply the difference between to aforementioned characteristics, therefore it is 97. However, you can approach those characteristics from completely another direction. We denote by xi1, xi2, and so on, independent random variables which are identically distributed and have distribution pk. And I remind you that pk was the probability that the ball hits box k. So to connect these characteristics with ball in boxes scheme, you can imagine them as the number of the box in which the k's box have fallen. So xi1 is the number where the first ball have fallen. It has number 100. xi2 is the number of the box where the second ball has fallen. It is 2, and so on. And then the number, the index of the last occupied box, mn, is going to be just the maximum among those entries xi1 and so on xn, because they just denote which boxes are occupied. And kn, the number of occupied boxes, is going to be the number of distinct values among xi1 and so on xn. So we just have a list of where balls have fallen, and we just need to find out how many unique boxes are there. So yes, it is the number of distinct values among xi1 and so on xn. However, our papers are not dealing with mn or ln, because for mn there have been already a lot of limit theorems proved, because of these characteristics. It is just the maximum of IID random variables. ln is harder to investigate, so we stay close to the number of occupied boxes kn, and we also consider some similar characteristics. First is even not similar, it's a generalization of kn. We denote it as k of I, and it is the number of boxes containing at least I balls. It is a generalization because if you put I equal to 1, you get the number of boxes containing at least one ball, and if there is at least one ball there, it's just the definition of box being occupied. And another characteristic which we are considering, we denote it as k star of I. It is a number of boxes containing exactly I balls. So the difference is with star, it is exactly I balls, without star, it's at least I balls. And when I is fixed, those characteristics are referred to as small counts. And in our papers, we were investigating only cases when I was fixed. So it was some number, for instance, I don't know, 200, whatever, but it wasn't dependent on n in those papers, which I'm going to discuss. Let's calculate those new characteristics for the same realization. So the number of occupied boxes we already calculated. The number of boxes containing at least 2 balls is equal to 2. Those boxes have numbers 2 and 100. The number of boxes containing at least 3 or at least 4 balls is equal to 0, because we do not have boxes with so many balls. And let's calculate small counts. The number of boxes containing exactly 1 ball is equal to 1. This is the box number 3. The number of boxes containing exactly 2 balls is equal to 2. Those boxes have numbers 2 and 100. And for the same reason, small counts for I, which are at least 3, is equal to 0. And what is worth mentioning is that those characteristics with and without star are connected between each other. So if you have some limit theorem for one of them, you can try somehow to transform results to another characteristic using those inequalities. So first one is, if you want to calculate the number of boxes containing at least I balls, you just need to take the number of boxes containing exactly I balls, add exactly I plus 1 balls, exactly I plus 2, and so on indefinitely. And if you want to connect small counts with in the backwards direction, the observation is simple. If you want to have exactly I balls, you need to subtract from the number of boxes which contain at least I balls, the number of boxes with at least I plus 1 balls. Okay, And this infinite occupancy scheme doesn't exist in vacuum. It has some applications. For example, you can apply it in biology. If you interpret boxes as species of animals or plants and balls as some animals or plants which you can encounter, for example, in some national park, then the number of occupied boxes would be the number of distinct species in this national park which you can encounter. Or you can apply...
Valeria, let me ask you, but in biology, maybe we have no such independency between the different animals, yeah? Maybe...
Okay, yeah, to apply it, we need to assume that the animals which we are taking out of there are independent, yes?
Yes, so we have to make some other suppositions, yeah?
Yeah, of course we need to...
In population biology, yeah. Mm-hmm.
Yes, we need to do additional assumptions, sure. But it's like with every mathematical model or something. I haven't encountered any mathematical model which perfectly represents something in real life. You always do some additional assumptions and simplify it somehow in order for it to work. Yeah. And so the same goes to the literature. You can interpret boxes as existing words in some language, let it be Ukrainian, and interpret balls as words which some author has used in all of his works. For example, you can take Ukrainian author Taras Shevchenko. Then the number of occupied boxes would be just the volume of author's vocabulary, and in simple words, it would be just the amount of words which he was using in all of his works. And another example is database optimization. If you have some database in which you have a lot of files and those files tend to repeat, you can interpret boxes as unique files and balls just any file which you have in this database. And then the number of occupied boxes kn would be just the number of unique files in this database. And in general, you can try to apply this infinite occupancy scheme to situation when you have some categories like species, words, unique files, and you have objects from these categories which tend to repeat, and you want to know how many unique objects you have in the sample. This version, which we were discussing, it is called deterministic version. And to highlight it, the most important, what we need to remember, that the nth ball is thrown at time n. So if we count time continuously, at time t, we will have integer part of t balls thrown. But there is another version of the scheme, which is called Poissonized. And before defining the scheme, let me introduce some pieces of notation. First one is we denote by pi a Poisson process on the negative half line with unit intensity. And we denote by S1, S2, and so on its arrival times. So basically, Poisson process is a counting process for sequence Sk. You can also approach a Poisson process from another direction. You can think of Sn as a random walk with exponential increments, and then Poisson process is the renewal process for this random walk. This another approach is going to be used while we will discuss some ideas of the proofs. I'll remind you later about it. So, in the Poissonized version, we change the time when we throw the ball. Now it is not n, as it was in the deterministic version, but it is Sn. And therefore, at time t, we have pi of t balls thrown, thanks to this, thanks to pi being the counting process of sequence Sk. And what is the reason behind introducing this Poissonized process? Denote by pi k of t, the number of balls which fall into the box k in the Poissonized version of the scheme. to connect it with what we had with process pi, we can notice that the total number of balls which we have pi of t is the sum of numbers of balls in the distinct boxes. Then, by the thinning property of Poisson process, those, let me call them sub-processes, pi1, pi2, and so on, are independent Poisson processes with intensities p1, p2, and so on. And I want to remind that pk was the probability that the ball will hit the box k. So what do we have? It's a Poissonized version. The number of balls which fall into different boxes, we denoted by pi k of t, are independent due to the thinning property. However, in the deterministic version, they are dependent. And it gives us some exemption from calculating, for example, covariances when we want to calculate the variance of number of occupied boxes. So if we denote by such bold k the counterpart of number of occupied boxes for Poissonized version of the scheme, we can represent it as a sum of indicators that there is at least one ball in the case box. And here, if you want to calculate the variance of this characteristic, since those indicators are independent, due to the thinning property, we don't need to calculate covariances. However, would we like to calculate variance for deterministic version, we would need to also deal with those double series and so on. And that is why mathematicians, while investigating the scheme, use usually this approach. At first, they Poissonize the scheme, then they solve the problem for the Poissonized version, and only at the third step, they try to bring the results to deterministic version, and this process is called depoissonization. And which tools can be used while depoissonization, we are going to discuss in the end, while we will discuss some ideas for the proofs. As for now, let's continue with infinite occupancy scheme, because of course it would be great just to assume that there are infinitely many positive pKs and that's it. But unfortunately, even central limit theorem is not known only under this assumption. We need to assume something more. And usually, those assumptions are stated not in terms of discrete probability distribution, but in terms of some function rho, which absorbs properties of this discrete probability distribution. A suitable function like this for us is counting function for sequence 1 over pk, which is defined as the number of indexes k, for which 1 over pk doesn't exceed x. Let's look at the behavior of this counting function at infinity. When x tends to infinity, we just need to find the number of such k's that 1 over pk doesn't exceed some large number. So the number of such indices also tends to infinity. However, it is known, and it's just exercise from analysis, that this counting function diverges to infinity slower than x. So the common assumption on discrete probability distribution is stated in terms of counting function, and it looks as follows. We assume that counting function is regularly varying of index alpha. And it means that it is asymptotically equivalent at infinity to x to the power alpha times some slowly varying at infinity function f. Now, what can be the value of alpha? Since we established that rho should be divergent to infinity, alpha cannot be non-negative. Cannot be negative, so it should be non-negative. On the other hand, since the counting function cannot diverge to infinity faster than x, we have that alpha cannot exceed 1. So the possible range for alpha is from 0 to 1, including both. And the first person who came up with idea of this condition was Karlin in his paper from 1967. We are going to mention a couple results from this paper later. And that is why the scheme is sometimes called in honor of him, because he gave this driver for the future investigation in shape of this condition. And let's look at some of probability distributions for which this Karlin's condition hold and which alpha we are going to get there. So if we consider geometrical distribution, which looks like this, and A is from 0 to 1, let's count this counting function rho. So we just need to understand for how many cases the inequality that 1 over pk doesn't exceed x holds. By simple operations, it is equivalent to k being no more than this value, and therefore a counting function at x is just the integer part of the right-hand side, and therefore it is asymptotically equivalent to logarithm x divided by such constant at infinity. So Karlin's condition holds with index alpha being equal to 0 and slowly varying function being this logarithm divided by this constant, which is slowly varying function at infinity. To give an example, when alpha is from open interval from 0 to 1, we can go to distribution, which is called discrete Pareto distribution. Here, psi is just normalizing constant, which guarantees you that all pk's sum up to 1. And in order for this probability, in order for sum of pk's to be convergent, you need to assume that b is more than 1. We do the same. We try to calculate a counting function. So by simple operations, we get that k shouldn't exceed this value. So counting function is just integer part of the right-hand side. So at infinity, it behaves as follows. And therefore, Karlin's condition holds with index alpha being 1 over beta. And since beta is bigger than 1, 1 over beta is from 0 to 1. And slowly varying function is just this constant to power 1 over beta. And constant is slowly varying function at infinity. And while looking for examples when alpha is 1, I do not know any common used probability distribution which has its own name to give us the example. However, you can come up with your own distribution, for which I do not know the name, but it looks like this. So it's just 1 over k plus 1 and logarithm k plus 1 to power beta. And constant is again normalizing constant. Then you cannot count counting function like directly in previous examples just to say that it's integer part of something, because you have here a function k times logarithm, for which it is hard to find the inverse function, but by some mathematical manipulations you can prove that counting function behaves at infinity like this. So in this case, Karlin's condition holds with index of regular variation being equal to 1. So we have x here, and slowly varying function is 1 divided by constant and logarithm to the power beta. And it is indeed slowly varying function at infinity. Now we move to already known limit theorems. And from what have been proven before, it is visible that limit theorems take different shape when alpha is 0, when alpha is 1, and when alpha is from open interval from 0 to 1. And I wanted to show you why does it happen. And we can see that it happens only while calculating such simple characteristic as mean of those random variables. So let's first analyze, I'll just show you the results for mean of number of occupied boxes. So in 1967, in this paper by Karlin, he proved that if alpha is not equal to 1, then the mean of number of occupied boxes is just the counting function times some constant, and here gamma is discrete probability distribution. Sorry, here gamma is gamma function. I don't know why did I say discrete probability distribution. But to move to the case when alpha is equal to 1, we needed first to define some function L hat. We define it as such integral, and you can put some effort into it to show that this function is well defined. finite for large enough t, and what's important for us, that it is slowly varying at infinity, and that function L, which was in the assumption that counting function behaves like this L times x to power alpha. So this function L is negligible comparing to this new function L hat. So for alpha being equal to 1, he proved that the mean of number of occupied boxes behaves at infinity like n times this function L hat. And we can move now to results for small counts. They were also proved by Karlin. So he showed that when alpha is from open interval from 0 to 1 and I is any positive integer, or when alpha is 1 and I is at least 2, then the behavior is pretty much the same. It's just counting function rho times this constant. And here gamma is gamma function. For alpha being equal to 1 and I being equal to 1, he showed that the mean of small count in this case is n times this function L hat, which we defined on the previous page. And how can we understand this result? So I here rewrote what we established. According to our assumption, when alpha is 1, counting function behaves like n times this function L, and this function L is negligible comparing to L hat. So what happens when alpha is 1? Why do we have such big of a difference when I is 1 and I is at least 2? When alpha is 1, so our distribution is heavy-tailed. According to result, which we have proven, L hat comparing to L is much, much bigger. Therefore, we are expected to have more boxes with exactly 1 ball than boxes with exactly 2 and exactly 3 and exactly 4 and so on. And in simple words, you can understand it as follows, that when you have heavy-tailed distribution, it is much easier to hit the box only once than to hit the box twice or 3 times and so on. And what about case when alpha is equal to 0? We didn't discuss it for small counts yet. And even as for now, it is not the behavior of mean of small counts in general when alpha is equal to 0 is not known. However, the trick with which mathematicians came up is to consider some subclass of this case. This subclass is called Thesession class. So let me define this class for you. We say that function f belongs to Thesession class, which for simplicity we will denote by pi, if for all positive lambdas and some slowly varying at infinity function L, such limit relation holds. And in this case, this function L is called an auxiliary function. And let's look at some examples. The simplest example of function which belongs to the Thesession class is logarithm, because if you calculate the denominator for the logarithm, you just get their logarithm lambda. So in order for this limit relation hold, you just need to choose this function L be constant 1. However, as a function which is integer part of t, even though it is slowly varying, it doesn't belong to the Thesession class pi, because you cannot come up with any normalization which is dependent only on t, so that in limit you will get logarithm lambda. It is known that every function which belongs to the Thesession class pi is slowly varying. So basically, in case when alpha is equal to 0, we do a compromise. Instead of considering all counting functions which are slowly varying, we consider only counting functions from this Thesession class. Of course, those are not all of the possible functions, but we didn't come up with anything better yet. And therefore, when I refer to the case when alpha is equal to 0, usually I mean by this that counted function belongs to the Thesession class. So the result which I found in survey by Knidin, Hansen, and Pittman in 2007 is as follows. They assume there that counting function belongs to the Thesession class with auxiliary function L. And also this auxiliary function is divergent to infinity and slowly varying. Then it is shown in this survey that the mean of small counts is asymptotically equivalent at infinity to this auxiliary function L divided by I, which is the number of balls which you want to see in the box. And there were much more limit theorems proved, of course, than just the analysis of mean of those random characteristics. First of all, the behavior of variance. There are the same theorems for the behavior of variance, and the only difference between mean and variance is that the constants are different. So, for example, here you would have the same function as this L, but you will just have another constant. And just like this, you have in every single case. Another limit theorems which have been proved and are more interesting because they involve something random are central limit theorems for the number of occupied boxes. It was proved by Dudko in 1989 under only assumption that the variance of the number of occupied boxes diverges to infinity. Central limit theorems for small counts were proved by Karlin in 1967 when alpha wasn't zero, and by Berber and Canadian in 2009 when alpha was zero. And here, as we established, by alpha being zero, I mean not completely this case, but the fact that counting function belongs to the Hahn class. And also there were proven some functional limit theorems for number of occupied boxes and for number of boxes containing at least I balls when alpha wasn't zero. In the case when alpha was from open interval from 0 to 1, the limit was just Gaussian process, and when alpha was 1, the limit was Brownian motion. However, we can ask ourselves questions. Okay, but what about some functional limit theorems when alpha...
Can I interrupt you with about this second line results? You said that functional limit theorem. So, what is the right normalization? What is the relationship with the normalization between time and like space value?
Actually, I'm going to show you some functional limit theorems for alpha being equal to 0, and I believe the normalization is approximately the same.
Normalization here in n times t, in the case when alpha between 0 and 1. N times t, linear scaling of time.
Not square root, yes?
No.
Okay, thank you.
Yeah.
Okay, thank you, Sasha. Yes, so... yeah, and also loss of iterated logarithm weren't proven as well. And this is the place where I'll start talking about those recent papers written by me and by my co-authors. So first one is functional limit theorem for the number of occupied boxes. It was proven by Sasha, Zakharka Bluchko, and me in paper which was published in 2022. And at first, let us denote by D the Skorokhod space of, it means that we have the space of functions which are continuous from the right and have finite left limits. So what we proved looks as follows. For all positive lambdas, we assumed that the counting function belongs to the Hahn class with auxiliary function L, and this auxiliary function is divergent to infinity and slowly varying at infinity. Then we showed functional limit theorem that the number of occupied boxes at such time, centered by the mean of this random variable and normalized by square root of such variance, weakly converges in a functional space to some process Z in the product G1 topology on this Skorokhod space D. And what do we know about the limit process Z? That it is centered stationary Gaussian process, and we found its covariance function, which is enough to define a Gaussian process. You can see the covariance function on the slide, and also in this paper you can find integral representation for limit process Z. It involves, I believe, white noise, and But I decided not to show it here because it's not the point of our talk to dig deep into integral representations.
There is a typo here because you mixed up the formulation of the previous theorem and the next theorem. Here there is just one process, so there is no product topology. This is just common J1 topology.
Yeah, you are right. You are right. Yeah, it will be product when we have here. Yeah, when we have d to the power n. Yes. Okay. So now passing to the case when we are going to have product G1 topology. There was a follow-up paper for small counts written also in 2022, where under the same assumption, we showed that small counts taken at the same time and with the same normalization and with the same way how we center them converge. However, here we have already vector process, so it weakly converges in a functional space to vector process XL in the product G1 topology on Skorokhod space in the power of n. And here, how do we have this limit vector process x1, x2, and so on is defined. It is, again, centered stationary. Okay, all of the coordinates of this process are centered stationary Gaussian processes with covariance function, which you can see at the slide. Of course, it's not very attractive, but what can we do about it? And also to define a Gaussian vector process, we need to define cross covariances for coordinates of this process. You can see those cross covariances at the slide. Okay, it looks bad, yes, but there is nothing more here on the right-hand side than just some simple functions of indices L1, L2, and of the arguments U and V. Then we asked ourselves question, okay, what about loss of the iterated logarithm? Nobody have proven them before. And this is what we done. There are two papers dealing with it. In paper which haven't been published yet by Darek Burachevsky, Sasha Eksanov, and me, we were proving loss of iterated logarithm was a number of boxes containing at least j balls. And in a paper which was published by Sasha and me this year, we were dealing with small counts. However, the results turned out to be exactly, so loss of iterated logarithm turned out to look exactly the same. That's why not to state the same theorems twice. I'm going to denote by x is a k or k star, but it doesn't matter because limit theorem looks the same anyway. So for the regime when alpha is equal to 0, we proved under assumption that counting function belongs to the Herrn class such law of iterated logarithm. Here we weren't able to prove it like in previous case, assuming that this auxiliary function L is arbitrary. However, we suggested two different behaviors for this function. First, that it behaves like logarithm to some positive power beta times some another slowly varying at infinity function L. Then the law of iterated logarithm looks as follows. This process x, centered by its mean and normalized by such function, has upper limit which is equal to this constant almost surely. And here, actually, we proved not law of the iterated logarithm, but law of the single logarithm, because in the normalization we have single logarithm. When L exhibits such such behavior, we proved in this case the law of iterated logarithm. So process x, centered by its mean and normalized by this function with iterated logarithm, has upper limit which is equal to this constant almost sure. And those results explain why we weren't able to prove law of iterated logarithm in the full generality for arbitrary auxiliary function L. It's because for different behaviors of this auxiliary function, we get either law of the iterated logarithm or law of the single logarithm. And maybe for another behavior, we'll get even something else. Passing to regime when alpha...
No.
Okay. Passing to regime when alpha is from open interval from 0 to 1. There were no complications in this case. So assuming that counting function is regularly varying of such index alpha, we showed that the process x, centered by its mean and normalized by this function with iterated logarithm, has upper limit, which is equal to square root of 2 almost surely. And I forgot to mention that, of course, alongside with relations for upper limits, we proved the same relations for lower limits, just with minus the same constant on the right-hand side. So, for example, in this case, we proved that the lower limit of this function is equal to minus square root of 2 almost surely. And the last case, regime when alpha is equal to 1. As you can remember from slide when we were discussing the behavior of small counts in this regime, when j is 1 and when j is at least 2, the behavior of small counts is different, and it is rejected in this theorem as well. So when j is at least 2, we proved this limit theorem just in the shape of the limit theorem of previous slide, that the upper limit of the same fraction is equal to the same square root of 2 almost surely. However, when j is equal to 1, we encountered some complications, but before discussing them, let's recall that when j was equal to 1, we introduced this function L hat. It was defined as such integral, and if j is equal to 1, we needed to assume some additional assumption on this function L hat. To be precise, we assume that for each small enough positive gamma, this asymptotic limit relation holds for this function L hat. Under this assumption, we were able to prove the law of iterated logarithm for this process x. But when this assumption 1 doesn't hold, then our proof gives you only the fact that upper limit doesn't exceed square root of 2. However, we were not able not to disprove the fact that this upper limit is square root of 2. So as for now, it stays as a mystery. And once we are going to discuss ideas of proofs, I am going to mention why did we need this assumption 1. And to show that function L hat for which this limit relation exists, I'm giving you an example. You can think of this function L hat as such exponent. Then just by honestly sitting and writing the numerator and the denominator, you can figure out that the limit is indeed 0. And now probably the most interesting part, the ideas of proofs. And I want to share ideas of proofs only for laws of iterated logarithm. So first step, as it was established, is Poissonization. Then the second step, we solve problem for Poissonized version. And third step is depoissonization. And we adhere to the scheme which we discussed earlier in our proof. So let me remind that in the Poissonized version, the nth ball was thrown at time ascent. So instead of considering number of occupied boxes for the deterministic version, we moved to the Poissonized counterpart of this characteristic, which is known by such bolt K. And it is the sum of indicators that in the kth box, we turned out to have at least one ball. Here, pi k of t, by pi k of t, we denote the number of balls which have fallen into the box k. And according to the thinning properties, those pi k's of t are independent Poisson processes. The next step is we need to prove what we wanted to prove, just not for the deterministic version, but for the Poissonized. And this was our first intention in those papers. However, it turned out that our proof works not only for number of occupied boxes or for some characteristics of Karlin's occupancy scheme, but it turned out to prove, for example, for Ginebra point process. So we decided to state this law of iterated logarithm for sums of independent indicators in general shape. So as for the second step, you can forget that we are talking about Karlin's occupancy scheme, and we're going just to talk about sums of independent indicators for the next couple of slides. So to do it, we at first need to denote events. So denote by A1, A2, and so on, independent families of events which live on a common probability space, and they are parameterized by non-negative time. And as promised, we consider sums of independent indicators, which we denote by Y. It is a sum of indicators that events AK of T hold. We assume that the mean of this process at each particular given time t is finite. Then from here, we can derive that this process is almost surely finite. And since the variance of Y doesn't exceed its mean, the variance is going to be finite as well. Under 6 assumptions on this process Y, we have proven law of iterated logarithm for Y in such form that the upper limit of this fraction is equal to constant and lower limit is equal to minus the same constant. Now here, in the normalization, we have this function f, and function f can be either iterated logarithm or single logarithm, depending on the regime. And the same constant as well depends on the regime. And we establish the regime while checking one of those 6 assumptions. You just have there the bisection of cases which you have, and this bisection you will see which constant you have and which function you need to have.
Valeriya, and of course you proved that this constant is not 0, yeah?
Oh, sure, yes. This constant is positive, no worries. Yes. Yeah. Okay. I'm not going to list all of those 6 assumptions. You would need to trust me that they hold for Karlin's for number of occupied boxes or for other characteristics in Karlin's occupancy scheme. But of course, it is thoroughly checked in the paper, actually in the papers. So how do we prove this law of iterated logarithm? We split the proof into 2 parts. In the first, we show that the upper limit doesn't exceed this positive constant. And in the second part, we show that it is at least the positive constant. But let's stick to the first part as for now. Our idea is to choose, instead of working with T, which is from a set of cardinality continuity, to work with sequence Tn, which has the cardinality, countable cardinality. So we choose sequence for which we are able to show such, I believe, 3 things. First one, that we are able to prove law of iterated logarithm substituting T by Tn. And in order to prove it, since we have countable set, Borel-Cantelli lemma is going to be a great tool. And to estimate probabilities which arise in this Borel-Cantelli lemma, we apply Markov's inequality for exponential moments. The next 2 conditions which we want from this sequence Tn is that we will be able to spread our result on the whole line, so not only for Tn, but for every T. We do it in such a way that we show that if T belongs to such interval from Tn to Tn plus 1, then the deviation between the nominator and between the nominator at moment Tn is negligible comparing to the denominator. The precise formula you can see at the slide of what I wanted to explain here. And the third step, we want to be able to change in the denominator Tn on T, and we do it with the help of monotonicity, which is among one of those 6 assumptions which I preferred not to mention. So once we are done with part 1, we move to part 2. And as I said, we want to show here that the upper limit is at least this constant, positive constant almost surely. Of course, we do not need to consider this upper limit over all t which tend to infinity, we can just choose some subsequence tau n, which is convenient for us. And now I'm going to define what do we mean by this being convenient. We want two conditions to hold for the sequence tau n. To state those conditions, let's at first recall that process y was the sum of those indicators calculated over all case which are at least one. We want to choose sets of indices Rt in such a way that this relation holds. And how can we explain this relation in simple words? So in the numerator, instead of taking y of t as the whole sum over all positive integers k, you take it only on the complements of those chosen sets. And you want this sum calculated over complements to be negligible comparing to the denominator. So basically what you want to say at this step is that all of the important mass of this process is concentrated on sets which you have chosen, on those sets R, and everything else what is outside is negligible comparing to the denominator. And here by this C we denote the complement, and also what we want from those chosen sets Rt, that starting from some moment R tau of n start to become pairwise disjoint. And then we want to prove, like after we show this limit relation, we need to prove this law of iterated logarithm. Just instead of considering their sum over all of the positive integers k, we consider a sum only over those chosen sets of indices R. And since they are pairwise disjoint, we are able to apply the converse part of Borel-Cantelli lemma with the version where events are independent. And the most convenient tool which we have found for ourselves there is change of measure. And I promised to tell you why do we have this additional assumption. When alpha was 1 and j was 1, it was stated in terms of this function L hat. Without this additional assumption, we weren't able to show that those sets R of tau n were pairwise disjoint. And now we are back to Poissonized and deterministic Karlin's occupancy scheme. Let me remind that by X we denoted either number of boxes containing at least or exactly J balls. And I'm going to denote by this bold X Poissonized version of this deterministic characteristic X. And I will refer to them as Poissonized X and deterministic X. And from the step 2, we have that the law of iterated logarithm for Poissonized version, so for bold X, holds. And now we want to have exactly the same, just instead of bold X, we want to have ordinary deterministic X. So first question which we ask is that, okay, are you able to substitute this mean of Poissonized version on mean of deterministic version? The answer here is simple, yes, because it is known that the difference between those means tends to 0 when n tends to infinity. And since our denominator is divergent to infinity, yes, we are able to do it. Second question which we ask, okay, we can substitute mean. Can we substitute the variance of Poissonized version on the variance of deterministic? We wanted it to do a lot, however, we didn't find any results like this, so we needed to prove on our own that we can do it. So the variance of deterministic version is asymptotically equivalent to the variance of Poissonized version under our regular variation assumptions, because in general, we didn't make to prove that it's true. And the third step is we are interested, okay, finally, we are able to substitute mean, variance, are we able to substitute Poissonized process X on deterministic process X here. In order to do it, we need to show that the deviation of deterministic process from Poissonized version is negligible comparing to the denominator. And how do we do it? The key observation there, is this equality. To understand from where do we have it, let me remind how did we define the post-niced version of the process. So in the post-niced version, you was throwing balls at moments Sn. So in this case, at moment Sn, you will have exactly n balls thrown. And if you couple those schemes, deterministic and post-niced, by the outcomes of the boxes where balls were thrown, you get that this equality holds almost surely. So here, instead of dealing with deterministic x, you can deal with post-niced x at moment Sn. And key tools for proving this limit relation is law of iterated logarithm for random walk Sn and Borel-Cantelli lemma, where we apply Markov's inequality for exponential moments to estimate the probability. And this is everything from me. Thank you for you listening to me.
Okay, thank you very much for your talk. And maybe somebody have questions or comments, please.
May I ask you a question?
Yes, please.
Thank you very much for a very interesting presentation. Very interesting results. My question is maybe you said about all these probabilities are positive. When we say that means that finite number of doctors.
I have hard times hearing you.
Unfortunately, we cannot hear you properly. Maybe there is some problem with your mic.
So my question is,
Now it's better.
Now it's better.
it's a partial case of this general. If it contains the finite number of forces P of the junior probabilities from starting from N.
Excuse me, again, we have a very big problem. Maybe we can switch to other questions from other participants, but you can put into the chat. You can print just your question, please, because we cannot hear you properly.
Second one. The probabilities are right here.
Yes. Can you please print your question into the chat?
No,
Okay. During you printed, we can discuss other questions and came back. Yes. Okay. Maybe other questions, please. Alexander Maratovich, maybe you want to comment something.
I have a question.
Oh, yeah.
Can I?
Yeah, please go ahead.
Можно на русском можно сказать чуть. Значит, что я понял по докладе, значит, доклад был очень интересным. Значит, что я понял, то, что рассказали, значит, поссонская схема более чем удобна, да, вот, чем детерминированная, я так понял. Это так получается? То есть поссонская схема более удобна, чем детерминированная схема, правильно? Значит, в чем тут удобность? Значит, вы сказали, что там есть, вот если рассмотрим хорошо поссонскую схему, там есть независимость, правильно? Так получается. А в детерминированном случае это вообще вообще не говоря, там не будет зависимости, там не будет независимости, правильно? Это так, я правильно понял?
Секунда. Так.
Да,
Я сейчас открою формулу, чтобы это было понятно.
Да, там была такая формула. Вы сказали, что там будет независимо. Там.
Так, да. Если мы рассматриваем детерминированную, детерминистическую, детерминированную версию, то там будут индикаторы, что в катой коробке, в катом ящике есть хотя бы один шар, и эти индикаторы, они не независимы, они зависимы, и корреляция между ними не нулевая.
Да.
Да.
Значит, ваша цель состоит в том, чтобы обобщить обобщить детерминированный случай, то есть сделать трансфер из детерминирования к пуассонскому случаю. Правильно? Так получается?
Да.
Да, понятно.
Ну, это не цель. Это как бы инструмент, который помогает доказывать в упрощенном виде там, какие-то теоремы, а потом вернуться обратно к детерминированной версии.
Ну, у меня есть вот такой вопрос, я не знаю, это может глупый вопрос, может. А давайте вашу схему можно ли рассмотреть, как-то вложить, можно ли рассмотреть такую, как модель вертящихся процессов? Почему я такой вопрос задаваю? Потому что вот у Александра Иксанова есть такие задачи, где он рассмотрел, вы, наверное, знаете, вот у него был такой результат, он применил, он доказал функциональную предельную теорему для вертящих процессов с активной иммиграцией. У него был такой результат. А можно ли как-то связать вашу модель с вертящим процессом? У меня вот такой вопрос. Я не знаю, это насколько хороший вопрос, удачный. У меня есть, появился такой вопрос. Как-то связать некоторые... То есть могу ли я допустим, знать некоторые предельные теоремы, функциональную предельную теорему вертящих процессов, допустим, для критически хороших процессов, применить или как-то... Если так, возможно ли такой случай вообще-то в вашем схеме, вот, в карлинском вложении Карлина? Вот, я не знаю, насколько хороший вопрос это.
Давайте, Валерия, я, наверное, отвечу. Это будет, наверное, более... давайте, пожалуйста, извините.
Хорошо. Я попробую быстро, а вы потом дополните, как хотите. У нас была, на самом деле, вот эта статья, на которую мы здесь ссылаемся, и еще одна, они таки были. Там мы рассматривали не просто схему занятости Карлина, а вложенную схему занятости Карлина, которая работала по принципу ветвящегося процесса, что у нас только в первом слое, я забыла русский. В первом поколении у нас была схема занятости Карлина, а потом каждый ящик этой схемы имел своих детей, которые были еще одной схемой занятости Карлина и так далее, и так далее. И на самом деле здесь функциональные предельные теоремы были доказаны именно для такой вложенной схемы, которая имела бесконечное количество поколений. И, кстати, поэтому здесь осталось это продукт. Я его забыла удалить, потому что это было как раз-таки с той теоремы, где у нас тут был еще индекс G, он значил поколение, и у нас тут был не просто один функционал, а векторозначный процесс. Вот, да, и так вот было.
Вот, то есть обобщение если вы начали говорить о ранних результатах по процессах Гальтона-Ватсона с очень активной иммиграцией, я не вижу, связи между процессами Гальтона-Ватсона с теми моделями, о которых рассказывала Валерия, но я вижу, и мы делали, действительно, мы размещали схемы занятости в последовательных поколениях взвешенного ветвящегося процесса. То есть взвешенный ветвящийся процесс Ну, вы можете знать этот термин, его очень пропагандировал Уве Рёслер в свое время. Фактически это мультипликативная версия ветвящегося случайного блуждания. То есть вот у нас вот таким образом, как устроены вершины взвешенного ветвящегося дерева, у нас таким образом были расположены ящики в последовательных поколениях. Вот. И то есть, ну вот в таком, то есть, что я хочу сказать, что, значит, установить связь с теорией ветвящихся процессов можно, но более сложных ветвящихся процессов, чем процессы Гальтона-Ватсона. Да, можно установить связь, и они были установлены, и была моя статья с Бастианом Малляном на эту тему, ну, там, для более сложных схем занятости. Да, ну это то, что я называю, да, схемы занятости на деревьях. Да, ну вот ответ такой.
Спасибо. Спасибо.
Okay, thank you very much.
Когда можно по-русски я спрошу свой вопрос. Можно?
Давайте, только чтобы
Да.
слышно хорошо было.
Да. Мой вопрос был, что эта схема содержит и схему размещения по конечному числу ячеек тоже. Если предположить, или вы предполагаете, что все вероятности положительные. Я просто пропустил мой вопрос.
Так, я все равно плохо услышала. Давайте я повторю, а вы скажете, тот ли был вопрос, что у нас есть бесконечно много положительных вероятностей пика. Так,
то есть они все положительные, да? А мы не можем предположить, что начиная с некоторого момента они... То есть ячеек конечно.
Ну, конечно, предположить это можно, но получится совершенно другая схема с совершенно другими свойствами. И вот эта схема, где было только конечное количество положительных ПК, она уже была исследована какими-то там русскими математиками, я помню, Колбин, Чистяков, Колышев, Чистяков, и там получились совершенно другие свойства этой схемы. Там, як сказати, поведінка? Поведение даже средних было другое.
Второе, это следующий вопрос. Эти вероятности фиксированные, да, у вас? А вот у меня вопрос просто такой, может быть, тоже не совсем корректный. А если эти вероятности тоже зависят от числа ячеек, от числа частиц или шаров?
От числа шаров вероятности зависят, да? Хорошо. Я не знаю, были ли такие статьи, где они зависели от числа шаров, но я точно знаю, что были статьи, где они были случайными величинами, и, возможно, там есть какой-то подслучай, что они могут зависеть от числа шаров. Но тут уже Саша будет экспертом, не я.
Ну, такие статьи были. Я помню статью Михайлова, по крайней мере, 81 года. И вот господин Мирахмедов, который задает вопрос, я помню, мне кажется, у него были пару статей, да, в которых тоже этот случай рассматривался, там, где вероятности зависят от числа шаров. Нет, мы этот случай не рассматривали. Ну, тут идеология будет иная, по-видимому. Идеология будет иная. Нет, мы этого не делали. Но я знаю, что такие исследования были. Правильно, вы же этим занимались, господин Мирахмедов.
Ну, да, занимался, поэтому и спрашиваю, что почему в последнее время я же только наблюдал, только фиксированное это рассматривается. Почему не рассматривается вот этот случай? Он что, почему не рассматривается?
Значит, если ответ очень прост, потому что не было ответов на совершенно базовые вопросы в простейшей постановке. И я могу очень легко объяснить, почему не было этих ответов, потому что эти ответы даже в простейшей постановке сложны. Потому что, например, там статья о законе повторного логарифма там занимает около 50 страниц в случае, и она очень техническая, то есть я понимаю, там уже сложно очень найти рецензента для нее. Да? Я думаю, что если сделать я не говорю, что это не будет интересная там, статья, задача, но я думаю, что уровень технических сложностей там, ну, он станет вообще очень высок. Ну, а главное, ну, должен быть запрос. То есть, имеется в виду, должен быть спрос на такие результаты. То есть я от вас первого слышу, честно говоря, вот сегодня, вчера, в последние годы, что там этим стоит заниматься, что это интересно. Ну,
Да, спасибо.
Okay, thank you very much. Maybe other questions or comments, please. If there are no other questions, let me say something. First of all, it was interesting for me to hear about the precise asymptotic because in 2011 I published a paper devoted to very different from the first loop subject. It was semigroups of random finite dimensional projections in Hilbert space. But these projections were organized as diagonal operators with random eigenvalues, which were driven by independent Poissonian processes. So to understand the functional behavior, to understand the limiting behavior of the width of different compacts under these projections, we need the asymptotic of like occupied boxes, exactly, because we have projections, yeah? Occupy a number of occupied boxes and moreover places where the boxes are occupied. So it looks that this things can be at least applied there. So Valeria, I have your mail. I will send you this paper. Just have a look. Maybe it can be.
Yeah, I'll take.
This is a first comment. A second is about the applications. I think that when you are saying something about applications, you have to at least mention what questions are discussed in these applications and why you want to get some mathematical results relatively to this just probable application. In this way, let me mention to you stepping stone model in population genetic theory, which is model related exactly again to occupational boxes and so on. So maybe it will be again interesting for you relatively to application of your model. Then the last comment is non-mathematical, but you mentioned that here we have a platform for young mathematician, and I must say that Valeriya previous talk was at the Skorokhod readings, which we organized for young mathematicians. So I just want to recall every participant that in the end of the semester we also will have Skorokhod readings, and not only Skorokhod readings, but about this in the future, where we can have a talk of PhD students, master students, and simply students who are doing mathematics and interesting probability stuff. Okay, then Valeriya, thank you very much. And our next speaker will be Georgi. Do you know who is the next speaker?
Yes, Vitaly Konarovsky.
Okay. So see you next week. Bye.
Bye-bye.
Thank you. Bye.
Thank you. Bye.
Bye-bye.
Bye-bye.